Well, good afternoon, class. Welcome to another wonderful video lecture on super complicated heat stuff that nobody gets. So we're going to start off with talking about what fins are and how they work and why they're important. So if you were to view this as a fin, the advantage of a fin is that you have more surface area to mass ratio. So if you just had a standard block, it's only going to have so much surface area to have convection around it on whatever sides, or maybe conduction with whatever you have interacting with it. But on a fin, you can have lots of these, and each one is going to increase your surface area. So where it gets complicated for the calculation is this fin is going to be conducting heat through its conductivity while it's convecting heat away from itself with all the surface area around it. And as you move from point to point, you're losing more temperature as you go, meaning that less and less heat is radiating off on the far end. So where this is important is if you design a very efficient fin, you're going to save the company that you're working for a lot of money or time or material, or you're not going to spend a lot of time over engineering a fin. You're just going to say, look, this is all we need, it's good enough. You're not going to stack too many fins in an area and radiate or drop off so much heat in the environment that you can't dissipate that heat fast enough. So it's important to understand how the energy flows through the media and how it is distributed away from the media into the ambient environment. So the way we do that is through setting up models and calculations. We have 4 basic simulations we can run with the fin. We have an insulated tip, we have the realistic model, then we have a fixed boundary temperature, an infinite length and a fixed boundary temperature. So if you look at our graph over here, the infinite length is going to say that this fin is just infinitely long and keeps on going. So as it gets closer and closer and further away, it's going to eventually be, the fin is going to be the exact same temperature as the ambient environment, because it's just going to go on forever. The black line represents a fixed boundary temperature. So it's going to go until it hits that fixed boundary temperature and then stay at that fixed boundary temperature, because it can't change the temperature than what it's in its environment. The important thing to notice here is our blue and green line, which represent our insulated and our realistic, are very similar to each other. So why that's important is if you look at the equation for those two, the realistic model has a very long, complex equation, and the fixed and the insulated model has a relatively simple equation. So if you can say this is pretty darn close to this is easier to calculate than this is. All of this information for these tables, or for this, is on table 2.2. It's page 119 in the book. So I don't want to go into all of the actual calculations for this. It's a lot of hyperbolics with the tangents and geometry. But once you get to this point, you just plug in your information. With the insulated tip, what we're basically saying is that heat is traveling through this fin. It's being convected away around the outside of the fin, and we're going to give it a false length. There's a chart for the false length. For this, I believe it's L divided by 2. For a round fin, it's D divided by 4. I can't remember what page that's on, but it's in the book. And we're simulating the heat loss through convection by adding a little bit of fin and then saying that there's just no more heat interaction on the back end of that because it's insulated. And so this false length right here is going to allow us to get rid of this big long equation. For the fixed boundary temperature, down here it's pretty simple. You have a fixed boundary temperature, so you just use that for the end. And for the infinite length, it's relatively simple because it just continues going on, but it's not as accurate as a model. So it's good for an approximation, but not for actual development or testing. When we get into this side over here, on page 121, we're looking at the fin efficiency, where it all kind of comes together and becomes important. And so if you look at the equations on the left, we use variables like big M, little m, and then stuff we already know like h bar and k and L for the length. But our big M is going to use our h bar times the perimeter times the cross-sectional area times the k of the material, square root of all that multiplied by theta s, where theta s is the difference between the surface temperature where this thing connects to something and the infinite temperature where it's going to end up out in the ambient environment. Little m is just the square root of our convection coefficient times the perimeter all divided by Ka. But again, all of these are given to you in word problem form when you actually work a problem. Take those and plug them in over here to our fin efficiency. We're going to have Q fin over Q max, where all of these equations, where all of these long equations are going to give us Q fin. By applying Q fin over Q max, we get the efficiency, and when we run the problem that we're given in the book, we run into a couple of different scenarios. So with the adiabatic or the insulated tip, I got 0.2736. For the infinite fin, I got 0.2742, and then for the realistic, using the very long equation, got 0.2739. So the difference between all three of these is about 3/10,000ths of a watt moving across an efficiency. So all pretty accurate, and some are much easier to calculate than others. So again, what it all comes down to is how realistic do we need for this model? If we're in very tight environments, then the difference of a few 10,000ths could make a major difference. If you're producing millions of these things, or if you're in such a tight confinement for temperature that it can break or destroy a system, then it really matters. But if you're just trying to approximate and say, that's pretty close to the ballpark, we only need to stay within a safety zone of like 10 to 20 degrees, then you can use a more forgiving, faster calculation. Another note is if you're running these things through MATLAB and you're trying to calculate for a very large system, the efficiency of the system, or the efficiency of your program, is going to be very important, because you're trying to calculate these equations multiple times over and over. And using something like the insulate, or using something like the infinite length with a very simple equation may be a good method then if you're running thousands and thousands of calculations. So I hope that this helped, and I hope I wasn't wrong.